going to just take what we just learned, which some of you would have seen that 171 if you've taken it or are taking it right now. So you should be familiar with it. But now we're going to take those curves and we're going to do calculus on the. So let's do that. Right. So generally, right, again, when we're plotting our parametric equations, right, I want to plot them on an XY graph, right? So it's not of interest for me to just have dx over dt and dy over dt. I want to see in general how y and x go together, so I can get the slope from there. Okay. So our goal, right? So we're going to start with derivatives. Maybe I'll address that here. So if I want to find the slope of my graph, right, what the parametric equations give me, right? Ultimately, I need to figure out what dy over dx is. Okay. Now, if we don't have the equation in terms of, y in terms of x, it's going to be a little harder to get this. But what we can do is I'm going to rewrite this. Actually, so we're looking for this, right? Let's think about dy over dt for a moment, though. Right? Just the derivative of y with respect to t. Right? I want that dy on top. Right? So how is this related to dy over dx? What would I need to multiply dy over dx by to give me dy over dt? Right? Again, this doesn't need to be too complicated, right? I can cancel out the differentials if I need to, right? So what do I multiply by to give me dy over dt? Dx over dt. Right? Because the dx will cancel out. And then I need dt, which will leave me with this. Okay? So we get dy over dt is dy over dx times dx over dt. But what do I need? Dy over dx. So if I want to get dy over dx, what should I do? I'm going to divide dx over dt from both sides. Which is going to end up giving me that dy over dx equals dy over dt over dx over dt. Should be pretty straightforward, right? I just take the derivative of the y part and derivative over the x part. Okay. Another way to see this is to kind of picture this as a sort of chain rule, right? Where we have maybe y is a function of x that has t in it. So I take the derivative of y with respect to x, and then I multiply it by the derivative of the x inside with respect to t. So that pops out. Okay. So if we want to find derivatives of our parametric equations, I just need to use this. Okay, I take the derivative of y and divide it by the derivative of x. Simple as that. Okay, so we're just going to get started off with an example. So this is going to be number 4. Okay, so number 4 in the book asked us to find an equation of the tangent at the point corresponding to given parameter. Okay, so this is the problem. The section gives us this, and then we'll do the problem specific. We get x equals the square root of t. We get y equals t squared minus 2t. And we're going to get, we want to find it when t So when I'm asking for a tangent to the curve, what am I looking for? So we don't want just the derivative, right? Whenever we're talking about tangents, yeah, we want to get we have a certain point. We want to find the tangent line is what it's asking for, right? I want to find the equation for the tangent line, right? The line that passes through that hits it at this point in particular. Okay, so when it says tangent, we're talking about tangent line. Of course, most of the work just goes into finding what the slope is. It's easy from there, but that's what we need. Okay, so right, in order to get the tangent line, I need two things. Those two things are slope and point. Okay, so we'll do that one here in a sec over here, the slope. But let's start with a point first, okay? So I want to figure out what the point is on this graph, on this curve that I'm going to be passing through. All right. So I know t equals 4 is where I want to pass. Okay. How do I figure out the point in particular? Plug it in, right? So when t equals 4, what's x going to be? X is 2. What's y going to be? Because we get 4 squared, which is 16. 16 minus 8 is going to get 8. So we get x is 2, y is 8. Okay, good. So that's our point, right? Now we need to figure out what the slope is. Okay, so to find the slope, right, we want dy over dx. So we're going to use the equation we just found to do that. So slope dy over dx, dy over dt. Okay, so what is the derivative of, all right, so y again is t squared minus 2t. What is the derivative of y with respect to t? Minus 2. Okay. And then I need to find the derivative of x with respect to t.
1 over 2.
Okay, so 1 over 2, and I'll write it as square root. Just like that. Okay, so you can find this derivative separately. So that might be a little more difficult, but in general, just find the derivative top and bottom and then divide the two. Okay, now I don't like fractions in my fractions. So I'm going to simplify this a little bit. So what can I do with this fraction? Multiply by the reciprocal. So we're going to get 2t minus 2 times 2 root t over 1. Okay. And then what's that going to end up looking like?
Over 2.
2 to the 1/2. I'll leave it as square root 4 to the 1/2. Okay, so we get this. Okay, now I want to find the slope at my particular point, right? So what do I do there? What am I going to plug in? What is it? We're going to plug t equals 4 in. So 4 times 4 minus 4 times the square root of 4. Okay. 4 to the 3/2, right? You can either do the numerator, then the denominator. Usually it's easier to do kind of the denominator of that fractional power first, which is over 2, so like the half power. So what is the square root of 4? 2. Good. Now, once I have that, I can raise it to the numerator. So 2 to the 3rd power. So what's 2 to the 3rd power? 8. Thank you. So 4 to the 3/2 power is going to be 8 in this case. Okay. Now what is, again, square root of 4 is 2. 4 minus 4 times 2 is 8. So we have 4 times 8 minus 8. 8 times 4 is 32. 32 minus 8. 24. Thank you. Awesome. So that's 24, right? I have my slope and I have my point. So what equation do I plug all this into? Planck's law form, good, which says y minus y naught or y1, whichever you want. Just as long as you're consistent. Y minus y naught equals m times x minus x naught. So we're gonna get y minus what? 8 equals 24 times x minus 2. Good. So I'm gonna get y minus 8 equals 24x minus, what's 2 times 24? 48. Okay. And then if I add 8 to both sides, what do I get?
24x minus
24x minus what? 40. So that's one problem. Okay. So really, this is a problem we've done before, except instead of you giving it y in terms of x, you have a parametric equation. Yes.
You have to simplify it.
Like this? Oh,
The answer.
I don't mind. I don't really mind that much. I mean, if it's like, if the numbers are pretty easy to multiply, then I don't see why you it shouldn't just kind of write it in the nice form. But it's also okay like that. Like I won't take off any points. Either way, it's fine. That's right. This is right. Okay. Good. We're not done with the derivatives yet, though, because I don't just want the first derivative sometimes, right? Sometimes I also want the second derivative, right? What if we're studying a curve and we want to understand concavity? Well, we could do that as well, right? And the way we're going to do that is, so I want to find, sorry, y. So we want to find our second derivative, right? Now, this is the same thing as derivative, right? This the derivative with respect to x of y over d. Anybody disagree with me so far? If I multiply the d's together, d to the second, then dx times dx is dx. Okay, good. Now, what I'm going to do is I want everything to be in terms of t, right? Now we know that dy over dx is the same thing as dy over dt over so we know how to find this once we have that, right? We should have it before we get to this step, hopefully. So I'm going to do something similar as what I did over there, right? Where we kind of introduce the dt, which here we use kind of a chain rule argument, but notice this is still the same thing as dy over dx if I just multiply by the reciprocal. So I'm going to rewrite this guy, this d over dx, as d over dt over dx over dt. Okay? And this is multiplied by multiplying dy over dx. So this is in the numerator, the denominator. This guy. What do I multiply it? Do I multiply it to the numerator or multiply it to the denominator? This is just, it's over 1, right? I haven't moved this to the denominator yet. It's just been multiplying, right? Okay. It wasn't a trick question, I promise. It's still in the numerator, okay? So I'm just taking d over dt over dx over dt times dy over dx over 1. Okay? So what's going to happen is that this d over dt is going to attach to this dy over dx. So I'm going to get d over dt of dy over dx. From there, my dx over dt is going to get put in the denominator. So I'm going to put that down here. So this is my second derivative. Okay. So what this says is that if I know the first derivative, which you should, I'm going to take the derivative with respect to t of that, what you found, right? So in that case, for example, we would have found the derivative of 4t to the 3 halves minus 4 root t. And then I divide it by whatever dx over dt is, which was 1 over 2 root t in that case. You give me that answer. Okay? Is that good here? This is the formula you want to use to get the second derivative. So again, this equals this guy. Okay, we're going to use that to do questions, comments, concerns. Uh-huh.
So
You just need dy over dx, which we got, right, which is right here, and we need dx over dt, which we, so you just take the derivative. Yep, absolutely. Okay, so it's going to be number 14. Okay. So jumping a bit ahead, but it's still in the same section. So doing the derivative. We're going to find dy over dx and d squared y over dx squared, first and second derivative, for which values of t, the graph, concave, okay, so we want to find the first and second derivative, and then we just need to ask to answer the question which value of t is the graph concave upwards. Okay, when it's kind of up like that. So our equation in this case is going to be t squared plus 1 for x. And our equation for y is going to be e to the t minus 1. Okay. First, we want to find dy over dx. Which, how do I find that? What is it? So yeah, so it's going to end up being 2t because we need to take the or actually it's not 2t in this case first. We need to take the derivative of the y part, right? First. Right, so we're taking dy over dt over dx over dt. So what is dy over dt? E to the t. And what is the derivative of the x squared? Good. So that is my first derivative. Okay. That's about as far as I can probably simplify it in this case. Okay. Now let's find the second derivative. Going to be the derivative with respect to t of dy over dx. And we're going to divide this by dx over dt. Okay, so we're taking the derivative with respect to t of e to the t over 2t over dx over dt, which we found earlier is supposed to be 2t. Okay, how do I take the derivative of e to the t over 2t? Quotient rule. Good. Okay, so what's that going to look like in this case?
2t minus 2t all over 2t squared, or 4t squared.
Yeah, 4t 4t squared 2c. If 2t squared is this, right? So other way, what would we find 4t squared? And that's all over 2t, like that, okay? Does this make sense to everyone how we got here? It's quotient rule, right? We take the bottom, 2t, times the derivative of the top, which is just e to the t, minus the top, times the derivative of the bottom, which would just be 2, and that's all over 4t squared. Okay, now I need to move this 2t part. So just like earlier, I'm going to multiply by the reciprocal, so we're going to get, maybe we can swap, I'll simplify at the end. 2t e to the t minus 2e to the t over 4t squared. If I want to fix that, what do I multiply it by? Close. 1 over 2t. Oh, gotta flip it, right? So since it's in, right, because we want to think about the denominator, this is like my big fraction here. This is 2t over 1. So when I multiply by the reciprocal, it's 1 over 2t. Okay. Now from here, there's a 2 here and a 2 here, right? For all of you who are tempted to cancel out this t with this t, you can't do that. Okay. This t and this t will not cancel, right? And the reason it won't cancel is because there's no t on this one. If there are t's on both, you could do that. But there's not a t on both, so you can't do that. Since there's a 2 on both terms, I can cancel that just fine. Okay. Right? If you have two things adding together, or two things subtracting from each other, in this case, if you're going to cancel something, that has to be on both things, right? I can't just cancel one and call it good, right? So in the end, I'm going to end up with t e to the t minus e to the t over 4t. Okay, good. So the question now becomes, when is the graph concave up? When is it going to be concave down? Right? Well, it's more just concave up. So let's try to answer that real fast. Okay. So who remembers how I started to figure out when the graph was going to be concave up? Right? What did I do?
You set the second derivative to 0, and then from there you get the equilibrium points. And from there, you can use test points to see when it's positive.
So I'm going to factor, that's great. I'm going to factor e to the t out. I'm going to rewrite this just because it's e to the t in both terms. So I get e to the t times t minus 1 over 4t cubed. And then we're going to set this equal to 0. Okay. So what values of t is going to make this thing equal to 0? What options do I have? 0 won't make it 0, right? 0 will make it undefined. We don't want that.
1.
Okay. The 1 will make it 0, right? Because it makes the numerator equal to 0. There's nothing I can do with e to the t to make it 0 either. We're not doing negative infinity, right? So t is 1 is the only thing there, right? But that's not the only point I take, right? We set it equal to 0 when we only got t is 1, right? Which is good. But there's other values I have to consider, right? So those of you who said t equals 0, you were right to say that, but not for the reason here, right? I have to include it because it makes my derivative undefined. Okay, so I include t equals 1 and t equals 0, but t equals 1 is the one that makes this true, but t equals 0 makes it undefined. Okay, once I have that, we're going to make a line, right? If you remember, we do a second, this is not the second derivative test. This is just a test when you're doing concavity. I'm going to have 0 and 1, my two values. Okay, and then like was said, we're going to test values on each side. Okay, so let's test a value before 0. If I test a number before 0 inside my function here. Okay, so let's take -1. Okay, is e to the -1 going to be positive or negative? It's positive, right? E to the -1 is still a positive number, right? Because e to the -1 is the same thing as 1 over e, which is still still a positive number, okay? That, and in fact, this is always going to be positive, so we don't really have to worry about it, okay? What about -1 in here? Is it positive or negative? Negative. If I put -1 down here, is it positive or negative? Negative. So we have a negative over a negative, which gives us a positive. So we are concave up this region. Okay. Let's test a value real quick between 0 and 1. Like from half, e to the t is still going to be positive. 1/2 minus 1, positive or negative? Negative. Good. 4 times 1/2 cubed. Positive. So it's going to be negative overall. So we're going to get this concave down. Okay. Last, we're going to do after 1. So 2, for example, e2 is still positive. T minus 1, positive. 4t cubed, positive. So the whole thing's positive. So we are concave up. Okay. So where am I concave up at? Yep. Fantastic. So then that'll be my answer. Okay. I won't do an example like this one right now, but those ask questions like this. If I want to know when I have a horizontal tangent line, what do I do? So what equals 0? The first derivative. So I would set e to the t over 2t equal to 0, or see what it's undefined. This can be equal to 0, but it can be undefined at t equals 0. Well, actually, I guess you wouldn't have a horizontal tangent line there. You would only set it equal to 0. I guess I was just thinking when it's increasing or decreasing. So in this case, we wouldn't have a horizontal tangent line, but in typical, you would say it equal to 0 and see what the value would be. Okay, so don't forget that stuff. We're only just slightly in a different context with parametric equations, but the same rules still apply. Okay, just because we're in Calc 2 doesn't mean we forget how to do increasing, decreasing, concave up, concave down, or any of that. Okay, chapter 3 is still important. Okay, cool. Let me go over here. So we're done with derivatives. Now we're going to talk about integrals. So let's go ahead and move forward. If only, the original, and or if only Calc 1 were this quick. Be like, here's derivatives, here's integrals. Okay, you're good. Let's see. So if I'm taking the integral, right, I want to find the area underneath my curve, right? And in that case, we're talking about y, right? We're talking about y in that case typically. So, all right. So typically, again, we're talking about y as a function of x, right? Or I'm just thinking about the area underneath my curve. So just like dy over dx here, I'm wanting to find the integral of y dx from a to b, right? This is still the typical setup we want, right? We want to work left to right, and we're wanting to use y as kind of the curve we're evaluating under, even if it might be a little wonkier in these cases. That's still what we want to use. Okay, so if I want to find an integral of a function and using the parametric equations, okay, this one's actually a little easier to figure out, I think, than the derivative ones are, right? I have dx over here, right? But I want to have t in here somewhere, right? Y, I can just plug in the t function, that's fine. But dx, I need to do something with, right? Okay, put dt down there. Can I just do that? There you go. That's how we do an integral. In terms of, now, of course, our bounds are going to be, and they usually are labeled as like alpha and beta when we're talking about in terms of time now. But this is how we evaluate an integral, or how we set up an integral with our parametric equations. You're going to have y times dx over dt, dt. Okay, so let's do an example. 32. Okay. Find the area enclosed by area enclosed by curve squared minus 2t, y equals square root of t, and the axis. Okay, so what's going to help us here, right? If we want to figure out exactly what's going on, right, we're going to need to probably graph this first. We want to kind of see what a graph is going to look like for us in this case. So we're going to so let's try to sketch this. Let's see what this curve looks like. So let's see, is there an easy way for me to solve this in terms of I think that's the easiest thing would be to do. Flip our equations in this case. Okay, so if I were to plot this, right, so we'll just take some points and kind of see what's happening. So I'll just take like some basic, obviously, so t cannot be negative. So t has to be like 0 or greater, right? Because otherwise the square root of t doesn't make sense. So I'm going to do, I'll just do a few points. We'll do 0, 1, 2, 3. Okay, why not? Some of them might not be the best values, but we can use them at least. So if t is 0, what's x going to be? What's y going to be? What is it? 0, 0. Good. So we're going to start the order. Nice. Okay. When t is 1, minus 1, 1. Yep. 1 minus 2. Good. Okay. What about t is 2? So 0, not 0, 2. It'd be 0 square root 2, right? I don't have the square root of 4. It's square root of 2. Okay. What about 3? We get 9 squared minus 6, or 3 squared minus 6, sorry, 3. And then root 3. And then we're going to have 4 squared, 16 minus 8, 8. And then we're going to get square root of okay, so so now I can plot these points, right? So we have 0, 0, we have negative 1, 1, we have 0 root 2, so that'll put us about here. We're gonna have 3 and square root of 3, which will be just a bit above where that root 2 is. And we're gonna have 8, 8, 2. 8, and we're going to go up to 2 exactly. Okay, so our curve is going to look something like this, right? Now, we're bounded by the y-axis, right? So, we only want the section of this curve that's bounded between my parametric equation and the y-axis. So here's my curve, here's the y-axis, right? This will keep going. We only tested a few points. So the only one we just want this piece right here. Okay, good. So we're going to need to make a slight modification, right? Because in this case, this would be a curve that looks like, you know, we're doing the area underneath this direction, right? Just our typical down to the x-axis, right? But now we're going to the y-axis, and so now we're going left and right. So instead of the integral of from alpha to beta of y dx over dt, I'm going to have x. that make sense? A little bit. Right, I'm not going to the x-axis now, I'm going to the y-axis. So I need to do my integral with respect to, kind of have it in terms of y, kind of have it in terms of t, just to flip the variables. Okay, but obviously if you were just given like an equation instead of go down to the x-axis, it's going to be your, that's fine. But we can use either. Okay, any questions on that? I want to make sure that everybody understands this. Whenever I read it earlier, I didn't realize instead of y, it's in fact x, but it doesn't change anything. We just decided to rewrite the equation. Okay, because we're going to look right now. Awesome. So we need to figure out our bounds, right? Which we just want to know when it hits the y-axis, right? Which is going to be at all the points when x equals 0, right? Because that's going to be, this is the y-axis is the same thing as the x equals 0 line. So if you didn't know the points, right, we would take x equal to 0, which would be t squared minus 2t, which would give us t0 and t2. But of course, we plotted some as well, and so we can see that clearly, right? We hit the y-axis when t is 0, and we hit the y-axis when t is 2. Okay, so either way, I think it's good to sketch it first to see what you're doing. That's what all of these problems are going to be about. But so those are going to be your 2 bounds. Okay, so we're going to go from 0 up to 2. Okay, so what is x in this case? Now, what is dy over dt in this case?
1/2.
We evaluate this integral. That'll be yours. Okay, so do you want me to finish this out? I'm running out of space here. I can probably move it over here real fast. I just underestimated how much I need, I guess. Maybe I'll finish it if I can finish it real fast. I'll bring it over that way. Okay, so we're gonna have, so we have the integral from 0 to 2 of t squared minus 2t times 1/2 root t dt, which then I can simplify as the integral, and I'll bring the 1/2 out from this root t here, of times the integral from 0 to 2 of, what's t squared over root t? T squared over root t? It's going to be t to the 3/2 power, right? Because I just take 2 minus 1/2. Okay, if I divide by a square root, I get t to the 3/2 minus 2, and then what's, yeah, t to the 1/2. Oh, it was, well, actually, it might be easier to write t to the 1/2 in this case. Okay, what's the integral of t to the 3/2? So we get 2/5, right? We add 1 to the power, and then we take t to the 5/2 minus, and then the integral of t to the 1/2 is going to be, so we have 2 times 2/3 t to the 3/2. And we're going to do this from 0 to 2. Luckily, 0 doesn't matter in this case because it just makes the whole thing go away. 2 to the 5/2 won't be the nicest number, but we'll work with it. Let's think about it though. 2 to the 5/2 power. So 2 to the 5th is 32, yes. So we get 32 1/2, right? Now, do we know any perfect squares that go into 32? 16. So we get 16 to the 1/2 times 2 to the 1/2, which square root of 16, 4. So we get 4 root 2. And so I'll put that here. So we're going to get, and this 1/2 is going to cancel out a couple of 2 zeros. So I'm going to carry that through as well. So we get 1/5 times 4 root 2 minus 2/3 times, now let's do 2 to the 3/2. I can do what is it? Right. It'll end up being 2 times 2. 2 cubed is 8. 4 4 goes into 8, so you can bring out a 2, so you get 2/3. Okay, and then from here we could just try to simplify a little bit, but in general this should be good. Just get a common denominator and it should come together. We get 4√2 on both of these. Maybe you could take that out, 1/5 minus 1/3. No. Okay, any questions on that? Very few of the problems are going to be like that one, but it's still good to see it, of course, to do it. Make sure we're on the right track. But that's how we do integrals. Okay, so if you're doing up and down, you do y dx or dt dt, right? Just like you're doing f of x dx. And then if we're doing, left to right, we're kind of bringing the curve to the y-axis or to a vertical line. Then we would do like f of y dy, which in this case will be x times dy. Okay, good. Keep with our topic of integrals. We're going to do arc lengths. Okay, so let's first talk about real quick the easy way to find this formula. If it's a nice equation, if it's nice and continuous and everything works as it should, right? We know that the integral to find a length, right, which from one value to another one, typically is going to be 1 plus dy over dx squared dx. Okay. Again, another way you can write that is doing dx over dy and dy if it was on the other axis. But in this case, this actually is a bit easier because it doesn't matter which direction you're coming from. It should evaluate the same either way. And the reason I say that is because I need to bring t in here. So I'll use the same trick where I just did dx over dt times dt, and I'll apply that here. Okay. Now I want to bring this dx over dt inside to my function. Okay, inside the square root, I guess. That's what I mean. Okay, so how should I bring that inside the square root? Good. So I want to take that dx over dt. I want to square it and take the square root, right? Because that, it's still the same thing, but it allows me to come to that square root now. But when I do that, I'm going to get the square root of, so I just get dx over dt squared here. Plus, and then what's going to happen with the dy over dx is the dx's are going to cancel each other out, but we're going to get a dt on the bottom now. So this is the arc length formula. Of course, you're going to have some, some one t to another t. Again, it could be another variable. It doesn't have to be t, but we'll use t here. But this will give you different, right? So this is actually this looks a bit more like your typical distance formula, right? Where you have dx and dy, right? But now we're taking both the derivative of both respectively. Okay. Good so far on that. We could also find this the same way, like if it's not a continuous curve and doesn't, has some weird quirks to it. We could also find this doing the same way we did when we proved arc lengths at first, and we were doing kind of the sum of the pi minus 1 pi stuff, where we're going to get both an f of x, like using the mean value theorem, we're going to get an f of t, dt delta t, and a g of t delta t prime squared for both, and then that'll come out and give us the same formula. So we don't need to kind of go through any of that again. We will just leave it here, but the book does explain it a little bit just in case. Need to be a bit more rigorous, but this is also for our purposes. Okay, cool. So let's use it. Do number 2. 2, which says to find the exact length of the curve. Nice. So. Good. So our curve in this case is going to be x equals e to the t minus t, y equals 4e to the t over 2. And we're going to go, because we need this particular values to go in between, we're going from 0. Good. So you could kind of try to graph it if you want. It's not as necessary here because again, our length isn't dependent on which direction we're going to the curve. I can just do it in general. So we're just going to use our formula to find this, right? So to find our answer to this length, right, we're going to take the integral from, what's our bounds going to be, we think? 0 to 2. Of square root of, now let's kind of address what each thing is, right? We need dx over dt and dy over dt. So what is dx over dt going to be in this case? E to the t. We also have a minus t though. What's the derivative of t? Minus 1. Good. Okay. And we want dy over dt, just so we get 4e to the t over 2. What's the derivative of 4e to the t over 2? You just bring a 1/2 down. 4 divided by 2 is 2. So we're going to put this. Okay. So now I'm going to take both of these expressions and put them here. So we get e to the t minus 1 squared plus 2e to the t over 2 squared. All that times dt. So we get 0 to 2. And then, so what is, how do I square e to the t minus 1? Foil it. Good. We don't just take the square of each term, right? We're going to foil it. We're going to have square root of e to the 2t. And then we do minus e to the t, minus e to the t. So we get minus 2e to the t. And then plus 1. And then what is 2e to the t over 2 squared? 4e to the t, fantastic. The t over 2 and the 2, those 2's are great. That's a lot. Et, okay, so we're going to get minus 2e to the t plus 4e to the t. So we're going to get e to the 2t plus 2e to the t plus 1, right? Because minus 2 plus 4 is 2. Hey, is there a trick here? That's a perfect square, right? With e in it, right? So I can write this as the integral from 0 to 2 of the square root of e to the t plus 1 squared, right? It's basically this thing, right? Except, right, because it was e to the 2t minus 2e to the t plus 1, but now it's got a plus. So similar to the other examples we did in that section. Okay, so we get this. So actually our examples are expanded a little bit more now. Okay, square root and the square cancel each other. So what is the integral of e to the t plus 1? Good. So we get e to the t plus t, and we're going to evaluate that from 0 to 2. So if I plug 2 in, what do I get? And I plug 0 in. Yeah, minus. So we would get minus, and we get 1 plus 0. So our final answer is going to be e squared 2 minus 1. Okay. Questions on that? Okay. Any problem that the book gives you to find exactly, or that I would give you to find exactly, it should work out in some way like that, or should be an easy use of. Okay, so if you're working on problems, whether that's on the homework or on the test, and you get something really wacky, it's probably not the problem. We want to check and make sure you did everything right. Okay. Because generally it should give us something really nice, okay? It's not going to be something that's like way too hard to solve. Okay? Good. Okay, one more. We still got a little more than 15 minutes, so this will be real fast. Okay? So if we've done arc length, what else do you think we could do? Surface area. Good. I can just use this concept to find the surface area of a curve, right? Or to find, if I revolve it, I can get a surface area out of it. Okay, so and even in that section, we're going to derive. We would derive these the same exact way. So if I'm doing surface area, right? Same work applies, right? Because we just multiply by the length, which we've already done the length before, right? And we're going to get the integral from alpha to some beta, right? Of 2 pi. And we're going to multiply this by, depending on which way we're going, right? If our radius should be up and down, then it'd be y, right? If it's left and right, then it should be x. I might write that one here in a bit, but we're going to get 2 pi y dx over dt squared plus dt squared dt. So this is about x axis, and this is y-axis. X dt quantity squared plus dy over dt quantity squared. Okay, so same equations as before, except instead of 1 plus the derivative of the thing, we're going to have the kind of the arc length piece in here, which is going to be dx over dt squared plus dy over dt squared to find our surface area in this case. Okay, does this make sense? Right? Set up the same way, we're going to have the length again, just kind of adding on extra detail now. So, do one example of this. Good. So, 62. So we're going to find some room. We did that. Okay. So we want to find the exact area. Of the surface. Obtained by rotating x. And our curve in this case is going to be x equals 2t squared. 2t squared plus 1 over t. Y equals 8 times the square root of t. And 1 is going to be less than or equal to t, which is less than or equal to. Okay, fantastic. So let's make it to the end. We're going to do this one, and we'll be good. Okay. So I want to find the exact area, right, of the surface, right? So again, we need to use our surface area equations, right? We're going about the x-axis, right? So I'm going from, what are my bounds? 1, 3, thank you. 2 pi, what goes here? It's going to be x or y? Y. Square root of, and I'll fill in some here a bit, but I can grab the x over dt squared plus squared dt. Okay, so what is, so we'll put y in, which is going to be h square root of t. What is dx over dt in this case? 4t plus -1 over, not 2t, but t squared. Okay, so we would bring that up as t to the -1. -1 would come down, and then subtract 1 from the power, so we get t to the -2nd power, or t to the 2nd power. I mean, it would be t to the -2nd, but then it come down. What's dy over dt? Okay, for yeah, 4 square root of t to the -1/2 power, which is, I can just write as 4 over. By the way, so we take 1/2, multiply it down in front. 8 times 1/2 is 4. T to the -1/2, but the -1/2 come down, giving us that. Okay, so we're gonna plug all this stuff in. So we're gonna get the integral from 1 to 3 of 2 pi times y, which is gonna be 8 times the square root of t, times the square root of, we're going to have 4t minus whatever t squared plus 4 over the square root of t squared. Okay. Good. So, let me erase this real fast, make sure we have room. But what's going to be, what's 4t minus 1 over t squared going to look like?
Squared minus 8 over t plus 1 over t to
1 over t to the 4th power. Good. Yep. So we're going to get, well, yeah, 4t over t squared is just 4 over t times 2 gives us 8. And then we have plus 4 over, so we get 16 over t in that case. Okay. And this is 3 of 2 pi, which I'll go ahead and there's an 8 on the front. So I'll multiply that up front with 2 and maybe the pi as well. I'm going to take it out. So we're going to get 16 pi integral from 1 to 3 of the square root of t. Okay. We'll probably multiply that in eventually. Let's see if we could simplify anything first in here. So we're going to get so I'll bring it up. We get 16 pi integral from 1 to 3. Can I combine any like terms in here? Yes, we can. T square root of 16t squared, then plus 8 over t, plus 1 over t to the 4th power. Okay, dt. dt here. Yes.
Why isn't it -8 over t squared?
Because you have to take the first term, which is 4t, times 1 over t squared, which will give you 4 over t, and then multiply by 2. So it's not t squared in that case. Yeah, it looks a little off, but our powers are actually evenly distributed. Like, so it's 3 powers between 2, -1, and 3 powers between -1, -4. So should be good there. Let's see. Let's go ahead. Maybe we'll take this t and multiply it inside, right? The square root of t. So we're going to get 16 pi integral from 1 to 3, 16t squared times t. Yep, this is inside the square root like this is, so we just multiply by t to the 1st power. Okay, t times 8 over t. T times 1 over t to the 4th.
1 over t to the 3rd.
Okay, now this may not have a direct connection point first here to do this, but this is still let's see. should be able to factor this in some way. Maybe we will. Yes, it was. I'm just trying to, I guess, yeah, that's true. Okay. Yeah, maybe we want to leave it before that. That's a good point. I was thinking to make it easier to put the T in there, but it doesn't seem like it would. So let's go back up real fast. You can feel free to try this out too. I think you can probably still work on something. Okay, so 1 to 3, we have square root of T. Now this is a perfect square in here, right? Because this is just this, but with a positive sign instead of a negative sign. So we're going to get the square root of 4t plus 1 over t squared. T. 16 pi, integral from 1 to 3. Okay. Square root and square root are going to cancel. So square root of t times 4t is what? Square root of t times 1 over t squared. And I might write that as t negative 3 halves in this case, right? We're taking t to the 1/2 divided by t squared, which is just 1/2 minus 2, which will be negative 3 halves in that case. Okay, and then dt. Okay, so then we're left with 16 pi. What's the integral of 4t to the 3 halves? Good. Because we take, so you do t to the 5 halves over 5 halves, so that 2/5 times 4 gives us 8/5. And then what's the integral of t to the negative 3 halves? Not 2 over 3, it'd be just, should just be -2, right? Because it'll be t to the negative 1/2 over negative 1/2. So I'll write that as -2, t to the negative 1/2, or I can, maybe I'll go ahead just for the sake of the work, right? It's -2 over root t. And we're gonna evaluate this from 1 to 3. Okay. Just plug in. Get our answer from there. So we're gonna get 16 pi times, let's see, 8/5 times 3 to the 5 halves -2 over root 3. And we'll have, so that's one piece of it. Minus, let's break it here. We'll have 8/5. I can finish, maybe I'll finish writing it down while we kind of wrap up here. But does anyone have any questions from the process here? This is a long problem, of course, because you can't really get a lot of good situations that are, that are going to be easy that just work out so nicely as this one does. But there you go. There's some calculus with parametric equations. Okay. So again, any questions for me? There you go. If you don't have anything for me, I'm going to stick around for a bit. If you have questions, I don't be anywhere, so I'm happy to help. So. Oh, you're fine. What's your question? I'll tell you right now, this answer you have right here. Yes. If you multiply by 2, though, you need to make sure that. Right, you apply 1/2 y squared plus y, and you multiply 2 to everything. I would you to make sure that 2 that's it. If you
Okay, so
you
we
could
have that stuff.
if you can solve that with the quadratic, solve for y, but you don't. Like, it's not necessary. If it looks a bit harder to solve for y, then you don't need to bother with it.
Oh, okay, because I thought I had to put that in the final answer, we have, like, put it with like y equals.
No, I understand. Yeah, absolutely.
Okay, well, that makes sense.
Yeah, absolutely. As long as even if it's implicit, it still solves the equation. It's just maybe not the most clear form, but that's okay. So.
Thank you.